Now it's time to figure out the same optimality condition, but using calculus. So the optimization problem that the consumer is trying to solve is to maximize their utility. So they want to choose their bundle Q1, Q2 to maximize their utility, but they have to do this subject to a constraint. They have to do this subject to the constraint that their income exactly equals the cost of the bundle. So the two choice variables are Q1 and Q2, so the consumer gets to pick these. And P1, P2, and Y are parameters. These are fixed. What we want to do is to solve for Q1 and Q2 in terms of these parameters. Rather than trying to have you do the Lagrangian method, which the textbook walks you through, I'm just going to have you do this via substitution. Remember, we had solved for Q2 in terms of Q1. Well, we could just as well solve for Q1 in terms of Q2, and then just plug that in and make this a function of a single variable, Q2. So we'd be solving something that looks like max Q2 sum U of Q2, right? So the utility would just be a function only of Q2 because we would have solved for Q1 in terms of Q2. So let's see how that works. So just like we had solved for Q2 in terms of Q1, we'll solve for Q1 in terms of Q2. It's the same exact thing. And so we plug that in and the problem becomes this optimization problem. And it's unconstrained, so there's no constraint to deal with. So we have an unconstrained maximization problem of a single variable. Maximize the value of this with respect to Q2. And what is this? It's just U of this function of Q2 and Q2 itself. Now, how do you solve these? If you remember from your calculus classes, the way you find an optimum is by finding the flat part of a function. So, for example, if you had a function that looks like that, then, so let's say you had Q2 here, and you had U on the vertical axis, then how would you find the optimal Q2? Well, the optimal Q2 is here, right? And why is that? It's because at this optimal Q2, the function's flat. The derivative is 0. To the left, the derivative is positive. To the right, the derivative is negative. Remember, the derivative is just the slope of the tangent. So think of yourself trying to climb a hill. How do you know you're at the top? Because you're at a little flat part. As long as there's a slope, there's somewhere higher you could go. In the process of trying to find the optimum, when you take the derivative of a function and set it equal to 0, we call that the first order condition. So if you want to maximize this function, which is a function of Q2, you're going to take the derivative of it and set it equal to 0. Again, that's called the first order condition. So that's our first order condition. Now we want to take the derivative of this thing right here. We're going to use a chain rule for that. So we're going to take the partial derivative with respect to the first term, which is just the marginal utility with respect to good 1, times the derivative of this thing with respect to Q2, plus the partial derivative with respect to the second good, which is Q2. So we just get U2. So this whole thing on the left side of this equation is the derivative of this with respect to Q2. So what's the derivative of this thing with respect to Q2? Well, y divided by P1 is just a constant. So we have the derivative of minus P2 over P1 times Q2. So it's just minus P1 over P2. So we have U1 times minus P1 over P2 plus U2 equals 0. That's our first order condition. So if we rearrange this, we get U1 over U2 equals P1 over P2. Or, written differently, it's the condition we've seen earlier. U1 over P1 equals U2 over P2.